All right, and so in this lesson here, we are going to continue looking at the different applications of your exponential functions. Okay, but in the way how I see that now, we are going to do those problems after we're going to be doing those problems after we have already found a model that predicts our an exponential function that models our natural process, either an exponential growth or an exponential decay right there. Okay, so once again, I'm talking about we're now in this lesson we are going to learn about those work we can do. We're learning about what we can do after we have already derived or have written our modeling function, our exponential modeling function to about the exponential decay or the exponential growth problem right there. Okay, and so in that way of what I'm saying, then I expect anyone who, at least for anyone who studies with me I expect anyone who studies with me to already view the video lesson where I spend a good significant amount of time introducing or teaching how you can write your own modeling function before you arrive at this video lesson. And so it is strictly required that you must learn from my other video lecture where I show how to derive or how to write your own modeling function for exponential growth and decay before we can move on in this lesson. Okay, but other than that, let's get started. All right. So now on this side of my board right here, allow me to, when we start getting into those problems, after you have already found the modeling function, and now before we get into doing the actual work, allow me to give the general structure of any of the problems we will be looking at. I'm talking about the general structures as far as the main steps, the main order stages, the main phases of your problem right there. Okay, so here's the way how I've been seeing it throughout my years of working with exponential functions, working with applications of exponential functions. So for any on any exponential function, all right, so on any exponential function application problem. All right, how about allow me to make it a little more precise for any exponential function application problem. The first step and the more important one is to be able to write your own function. Okay, so step one or stage one or phase one, that's why I'm calling that a one right here. Okay, and it's a certain order of the steps right here. So the first important step is to write the modeling function. All right. First important step is to write your own modeling function, your own, and of course here we're talking about the modeling exponential function that models your quantity, your population, whichever that's growing or decaying exponentially. Okay, so that's step one right there. Write the modeling function. Okay, as an exponential function, of course. Okay, because that step is so important, at least in my experience and in my the philosophy of seeing these application problems on exponential functions. Then being able to write your own modeling function is so critical. And once you have identified your modeling function, then we can start doing a lot of other work. Okay, but so now, the whole point of writing your modeling function, and then when I was saying writing your function, sometimes you don't have to write, but you can just simply identify. Another way of saying it, you can just simply identify the modeling function as an exponential function. That's stage one. But so now, back to what I was in the middle of saying, The whole point of coming up with a modeling function is to predict. Because, we are living in a world where there's time as a parameter, as a variable that's running connectively behind the scenes. Okay, so time is the rule for everything. Time is what controls everything. And so at this time moment right here, you have a bacteria, and then in some times later, in some t years or t hours, in some t months later, the bacteria culture is going to grow. Okay, right now you're looking at a radioactive element, and then at some time later, it's going to decay and keep disappearing itself like that. Okay, and so time is what answers how much amount we have grown over time, or time is what answers how much we have lost of a quantity over time. Okay, and so we come up with these modeling functions here to predict how much we will have in the future, or how much we will to have remain over a certain amount of time. Or we can also predict how much time it takes to arrive at a certain amount that as we expect that we would like to reach. Okay, and so those are all of the different scenarios, but those I categorize them, I classify them as the stage 2 right there. So after you come up with your modeling function, the next stage here, the next step here, and this is where we're going to focus in this particular video lesson. So stage 2 here is to make, all predictions. All right. And that's why without coming up with a proper exponential function, or without coming up with without being able to write a proper and precise exponential function, or a good exponential function, a good modeling function in general, then we won't be able to move on to stage 2 right here, where we can make all predictions, the different kinds of predictions. And that's the reason why, for anyone who arrived at this lesson, I assume that you have already viewed and learned from my different lessons that I posted earlier, that I have delivered earlier, about how you can write your modeling function as an exponential function. And I believe in that video lesson there, I've spent a significant amount of time right there, because I believe I've shown almost every little detail about how, and every little situations about how you can come up with your exponential function. Okay, and so now allow me to assume that you have been familiar enough, anyone arriving at this lesson, you have been familiar enough with step 1 right here, with stage 1, that you have to write or be able to identify your function. And now we're going to focus in this lesson about how we can make the different predictions. All right. And then, so now for the rest of the video lesson here, here's the plan for the rest of the video lessons. I will be taking you into what I so-called the different scenarios. I mean, each problem for us here, now you can pretend that you are a scientist. You can pretend that you're a businessman who is working with, with a financial math problem where your money is growing. Okay, you can pretend that you are a chemist. You're working with chemical elements that's decaying over time like that. So pretend you're either a scientist or a business person a business professional who's working on the financial math problem. Okay, and then we're gonna focus on, after you have already come up with your function. Okay, we're gonna make all kinds of predictions, and this is where as I said earlier, I'm gonna take you into different scenarios. You're gonna be put into different scenarios. Okay, and then with these scenarios, any one of the scenarios that I'm about to bring up will be quite independent from each other. So in other words, whatever scenario I teach first in the lesson here does not necessarily have to always be the first one in order to learn the next scenario. When you're going through these scenarios right here, I just want to emphasize that any of the scenario can be learned independently. It has its own independence on it. Okay, and you will understand exactly what I mean as we get into it. Okay, and then as we are into each of the scenarios, I will be able to bring in a problem 1, a problem 2 in each of the scenarios. And again, even I call them some problem 1, some problem 2. Each problem is one little scenario on its own, like that. That you don't have to particularly do problem 1 in order to be able to do problem 2. Okay, so for that reason, you won't. I'm stepping a little bit out of my style here a little bit. That So usually in many other video lessons, I go with example 1, example 2, where the order of the examples relates the examples together. But here, each problem I introduced is one independent problem on its own, completely one independent problem on its own. Okay, but other than that, let's get in. So only keep in mind one thing. I already assume that anyone learning in this lesson is already well familiar with how you can write or at least identify your own modeling function. We're going to focus on in any of the scenario I'm bringing up right here, we're going to focus on how we can make the prediction. All right, so now let's look into the one of the scenarios. I shouldn't say first scenario or second scenario. Let's look at one scenario here. All right, so one scenario I would like to introduce here is about as far as making the prediction. Most naturally, we just once we have already come up with the modeling function, we just want to find or estimate. Okay, we just want to find or estimate a future value. A future value. Okay. Because again, as I have explained, the whole idea of coming up with a modeling function is that so that we can make a prediction. Because time is one important variable, one important parameter, whichever way you want to put it, but time is so important. And then as time goes on, everything is changing. Every quantity that we're looking at, that we're studying, is changing. Either it's a money quantity, it's money amount, or it's a population of bacteria, or it's an amount of chemical substance, okay? Or it's a value of the value of a car that's losing on its own over time. Any quantity is changing over time, and for that reason, so one scenario here is that once we have come to identifying and already identify our modeling function, we are going to look at how we can find or estimate a future value. Hey, how big is the population of bacteria, the 10 months later? How big is the population of how big is the population of that country in utopia, 20 years from now? That's what I generally means by that's what I generally meant by a future value right there. All right. And so now this is what we're in right here, one of the scenarios. And this should be the most natural one once we have come up with the modeling function. We want to find or estimate a future value. And if you are a business professional working on your financial math problem, today you're bringing into the bank a certain amount and you want to leave it there to invest. You want to find out how much your money will grow to in 20 years from now. It's again another scenario. It's among the scenarios where we want to estimate or to find a future value of our quantity, of our population that we're currently looking at. All right, and so now I am going to turn over to the computer screen and I'm going to bring up problem 1. Okay, and so I call that problem 1, but really it's just one of the problems in this scenario over here where we want to find a future value. Okay. All right, so here we go. So now in this problem, we're looking at a population of bacteria is growing. So what we have here is a population, a quantity, okay? Because there are a lot of bacteria in this population, and so we regard to that as a population of bacteria, okay? And now I can undo that highlight. A population of bacteria is growing according to the equation P of t. It's a population size as a function of t equals 1600 times e to the 0.21 t. All right, and then t is the variable for time that's measured in years right here. Okay, and so now before I get to reading the actual question, now allow me to swing back to the board and try to align and try to point out how this problem aligns with the stages that I introduced earlier. All right, and so as I was introducing, in the way how I see any of these problems, the first important step is to either identify or to be able to write your own modeling function as an exponential function. I keep that word identify over here, and then I leave the word write, because to me, being able to write the function is even more important. But then there are times, like say for example in the problem I just showed right there, we don't have to write the function because the function was already given. And so in that way, we simply just read through the problem and be able to identify where it was out, where it is to be the function that we can use. Okay, so that's why big important step right here. We must always be able to identify or write the modeling function as an exponential function, supposedly in these kind of problems right here. Okay, and so now back to the wording on the problem. And so now as far as stage 1 or step 1 to identify the modeling function, this highlighted function right here is already our modeling function. Or in other words, we already had the modeling function given. So in this problem right here, one more time, back to the general structure of the problem right here, stage 1 is already completed, has already been completed for us. So think about if we're an analyst or a scientist who already got that function given to us, then we're going to take on with that function. We're going to take that function and work on the next step. So we're going to be now those scientists that work in the next stage here of the problem, stage number 2, where we can start making the predictions, the different kinds of predictions. All right, and so now once we're clear with the plan, now we can start reading into the actual question. And so this is, in this problem, there's only one question. So now we know that this is our modeling function. So the population at any time t is 1600 times base e raised to the power 0.21t. All right, so now we want to find the size of the bacteria population in 10 years. All right. And then I also highlighted that the t variable for time here is measured in years. All right. So now on my board here, I will keep this major title of the subtopic or title of the scenario here. But in this particular problem that I brought in, then our function was given already. Okay, so stage 1 is done. We don't have to spend our efforts to get stage 1 stage 1 done for us, but it's already done by someone else for us. We're just taking that 1600 times e to the, and this is base e. And so at this point, after you have learned about, have learned from my lessons about there's a continuous growth model or a periodic growth model, you should be able to tell, or at least to raise your own awareness about what kind of model this is. But that's not even important in this particular problem because the model was already given to us here. Okay, it's base E. So 1600, just keep in the back of your mind the meaning of any of these numbers, that's all. For example, right now as I'm writing this down, for anyone viewing this lesson, you can start being aware about what this 1600 as a coefficient in this function means in the actual problem. Okay, and now 1600 times e to the 0.21t. So that's our clearly exponential function, but models the size of the population over some t years. At any t years, after some initial amount at start, and now I'm using that term initial amount of start. So hopefully I trigger some of your curiosity because the information regarding the initial amount is already included in this given the function already, in this given model already. Okay, but now again, this function here helps us or tells us how we can predict, okay, tells us a way to predict how big the population of bacteria in some t years, okay, in some t years after the initial amount, okay. And so in this way, how we have already seen, in this way that we have already had our modeling function, then the problem surprisingly turns out just simply as easy as find or evaluate the wording of the problem did not necessarily have to write this, but we just write out from this problem. We have that as given. Okay, we have that as given, and now we just want to find or evaluate P of t. Okay, at t equals 10. That's what it is. 10 years. Find the size of the bacteria population in 10 years. And t is the variable that's measured in year. Okay? T is in years. All right, t is in years. And so now we want to find the size of the population, so that just simply means evaluate the function value. It's already given, the function's value at the given variable's input right here, t equals 10. Or in other words, just even long story short, we just want to evaluate here, we just want to evaluate P of 10. I've been beating around the bush a lot to the point that maybe some of you viewers out there already lost your patience, but I just want to really emphasize how easy that is once we already had the function given. Okay, and so now that's all there is. I'm going to go ahead and substitute t equals 10 into this given function. So now 1600, okay, times e to the 0.21 times 10, because that's t is the variable that's measured in years. And now we're looking at how big that population is in 10 years from now. So I mentioned a little bit about 10 years based on 10 years from what time point, from which time instance. 10 years from the initial amount that we start. It's the way how it is. And of course, all of this information was already introduced back in that lecture where I show in depth how you can write your own modeling function as an exponential function. Okay, so here only I only need to and allow me to only just quickly remind anyone. But see, this one right here, this value as a coefficient. And now earlier I was asking you to have in the back of your mind about what that is, about the meaning of that 1600. But now at this point, assuming you have had enough thoughts right here, this is the initial amount right here. Okay, in case you haven't been concerned, this is the initial amount at time 0. And so when we start studying about this population, we are starting out with 1600 of them. I mean, we don't have to worry about how the scientists count these bacteria. Of course, we use microscopic devices to count these bacteria. But now, assuming that we know that's about how big we've had initially, 10 years from that point that we start our study. Okay, if we're one of those scientists, then how big is our population, or what's the bacteria count in that population? So the number will be whichever comes out from this calculation right here, from this function, this function's value when t equals 10. That's all there is. And I already had the function the setup with t equals 10 successfully substituted. So I'm just simply swing over to the computer station here and show on screen the calculation with my TI calculator. That's all. Okay. All right. So here we are on a standard TI calculator. All right. So now all we have to do is 1600 times, and on the keypad we're looking at this e to the x function right here, right above that key ln. So second ln that will bring in e to the x. So now it's in the power of the e function, 0.21 times 10. And now we are ready to hit enter to come up with the final evaluated answer over here. So 1600 times e raised to the power of 0.21 times 10. All right, and so in this value right here, this is the final value, 13,065.87. So we can, well, this is a bacteria count, so 10 years, now we can, it's a count for an actual bacteria, for the number of actual bacteria, so it's best that we round to the nearest integer, okay? And then, of course, if just be aware about the rounding situation on any of your own applications. When you're working with a scientist, make sure you know how the scientists, how the community of scientists out there expect you to round. So here in just this lecture, allow me to round to the nearest whole value above. I mean to the nearest whole value. That's all. So now on the board, I'm looking at, in 10 years, we're looking at P of 10 equals 13,066, okay? It's just the nearest integer, not necessarily above or below, but just the nearest integer rounded from this value right here is 13,066. So the count of bacteria in our population 10 years from that initial amount right there will grow to 13,066 of them. All right, and so it's just simply, that's how simple it is. Okay, and we're in again in one of the scenario where we're just gonna use a modeling function to what we have just done here. Even though I'm using that precise term, find or evaluate, but really it's just this is an estimate of how many bacteria we have, okay, in 10 years. Because again, the reason, the most solid way of saying it, the most accurate way of making the statement is that we're estimating. Because of course, a modeling function here only helps us predict. It's not telling the truth of reality out there, because in reality there may be some bacteria is dying throughout the whole 10 years. 10 years is a lot of time. So we're only considering the theoretical case here where, you know, which is growing and growing and growing and no bacteria is dying. Okay, but in other cases, I mean, in reality, there may be some bacteria dying. So that's why this number here will permanently stay as an estimate. Okay, but mathematically speaking, it's a problem where we evaluate our modeling function at the given input for the variable t equals 10 in this scenario over here. All right. And so now in this scenario, we're done with this particular problem. Let's look into another one. All right, so again, we are still going to find or to estimate a future value. Okay, so now allow me to bring in a different problem right here in this scenario. All right, so here we go. So now in this problem, let's spend some time reading the wording description of the problem right here. A radioactive substance decays exponentially. A scientist began with 100 milligrams of this radioactive substance. After 35 hours, 50 milligrams of the substance remains. All right. And allow me to make a quick pause here. Well, of course, the question of the main question being asked is here. How many milligrams will remain after 54 hours? But so now back to what I was saying about taking a pause here. I would like anyone to have some close attention. In this problem, okay, and if we are try to align this problem with the two major stages that I've listed on the board here, then in stage 1 here, we did not have the function given in this particular problem. So in some other problem, we have the function given. We have the modeling function given, then we just simply need to identify the function throughout the worded description of the problem. Okay, but in our problem currently we're working with, the function is not given yet. The modeling function is not given yet. So that's where we have to be able to write the modeling function here. And this is the reason why, you know, you need anyone viewing this lesson must have already viewed my lesson where I specifically focused on the skill of how you can write your own modeling function. Okay, precisely speaking, how you can write your own exponential function as a modeling function, okay, from the given data. So in this problem, what we have here is simply just data, and now we need to, and the problem didn't even ask for it. The problem did not even ask us explicitly that, hey, you have to write a function, but it is our responsibility to write the function because the function was not given. Okay, so here we have to write a function. All right, and so now let's spend some time identifying our function or writing our modeling function. Okay, so now in order for us to write, and again, I just want to emphasize that nowhere in the problem asked us to write the function ourselves, but it's just our default responsibility that we need to know what the modeling function is so that we can we can answer, so that we can answer how much, or how many milligrams will remain. So this is a future amount right here, some amount after 54 hours. And that's why in order to answer this question, we need to be able to come up with our modeling function. All right, and so now, in order to get into this problem, so if you connect our study here, our the lecture here with that lecture where I was teaching about how we can write a modeling function, then we have a choice between using a periodic model, and the problem we're specifically looking at here is a decay problem. But it doesn't matter, it could be a decay problem or a growth problem. But there's always two choices. Okay? One choice is to use the periodic model, and the other choice is to use the continuous model. Okay? And then at some point, quite a few instances throughout the lecture where I was showing about how we can write the modeling function, I was making my statement that the continuous model is the one that's much more commonly used among the scientists out there, including the financial experts. All right, so now in that way, allow me, for this particular problem, allow me to stick with the continuous model. The continuous model. I'm heading out for the continuous model, meaning it's base E. I'm going to use base E instead of the periodic the model with some base being in the form of a 1 plus or. Okay, so again, briefly, we have two choices. One choice is to write our amount right here. This problem is about the quantity of the radioactive substance. So I'm going to call that Q of T instead of P, because P for me it just means a population. So Q of T can be some initial amount times 1 plus or, if we know the decay rate in this problem, if we know the decay rate, and it should have been minus 1 minus r to the t. This is the periodic model right here. Or we can go with Q of T being the initial amount times e to the k t, with k being a negative value, because this is a decay problem. Okay, and this model here is a continuous model. So back to what I was saying, I'm just gonna show anyone how to derive, how to write this continuous decay model over here to be one, because it is much more commonly used out there, and it's a lot more convenient out there to use. All right, so that's the plan right there. And outside of this lesson right here, you can feel free to, on your own time outside, once you're done with viewing this video right here, feel free to come up with your own periodic decay model on your own right there. Okay, and once again, all of the proper steps have been taught in my earlier lecture, where I was showing how specifically on that skill of how you can write your own modeling function. Okay, and so now this is not what we're paying attention to. We're gonna pay attention to this. It's base E. All we have to do now is identify the rate, the continuous rate right here, the continuous decay rate, and then we need to identify from our given information the initial amount. All right. And so now in our problem here, rolling back to the main description of the problem, a radioactive substance decays exponentially. A scientist began with 100 milligrams. All right, so the wording is making it so clear. That scientist, whoever that was, began with 100 milligrams. So I can simply take this information right here as our initial amount. So in other words, we already have right from the problem, Q sub 0 must be 100 milligrams. 100 milligrams. Okay, and then now, and so again, we are on our way to get through with step 1, stage 1, so that we can write our own modeling function, even though the problem did not ask us specifically for that. But we have to get it done before we can answer the actual question stated here. Before we can answer the actual question stated here, then we have to be able to write our own modeling function. Okay. And so now, moving on to the next piece of information. It says after 35 hours. So now this means when t equals 35, because time in this problem, even though not directly mentioned, but time in this problem is by default is measured in hours right here. Okay, and so because that information is given right there. So after 35 hours, 50 milligrams of the substance remains. 50 milligrams of the substance remains. Okay, after 35 hours. And the reason I know to identify that our time variable is measured in hours, because even the question itself is asking, focusing on 54 hours, where time is measured in hours right here. And so back to this information, after 35 hours, 50 milligrams of the substance remains. That means, now, mathematically speaking, as a mathematical expression, see, we're looking at the following. Well, Q of t is the quantity in some t hours, the quantity in some t hours. This is our general function right here. But Q of 35, after 35 hours, okay, we have 50 milligrams of the substance remains. It's a decay process, so of course as time goes on we're losing. So right at that instance where it hits 35 hours after the initial amount, then we have 50 milligrams remain. That means this is a future value already given to us. This is a future value given to us. This is whatever the value that came out after 35 hours. It's some given information. So now, upon having this initial amount right here, back to what we have already learned. From what we have already learned, and we're talking about our function Q of t must be 100, generally 100 times e to the kt. Okay, and then now utilizing this information into our currently found equation, currently halfway found equation, Q of t equals 100 e to the kt. And so when t equals 35, we have outputs. Q of 35 equals 50. So that means now I'm looking at 50 equals 100 times e to the k times 35. Because according to what this says, Q of 35 means 100 times e to the k with t substituted by 35. We have seen all of this back in our major lecture. In our lecture where I taught about how we can write our own modeling function. And then this is the output, the output of the function when t equals 35. So that means now we're right from that relationship, right from that given information, we derive this based on our function currently found to be 100 times e to the kt. And now we are ready to find the value for k right here. We can rewrite this expression as so this is 50 times 100 e to the 35k to make it look a little better. And so now in the next step, I am going to divide both sides of our equation here by 100. And so now 50 on the left hand side equals 100 times e to the 35k. Dividing both sides by 100, I am looking at e to the 35k equals 1/2. E to the 35k equals 1/2. And so now, just like how I have explained thoroughly in my lecture about how we can write our modeling function, when we have arrived at this equation, which is in exponential form, we can re-express that. We can rewrite this equation in logarithmic form. And so now I'm looking at natural log of 1/2 to equal 35k. Okay, natural log of 1/2 to equal 35k. And so now apparently at this point we can easily find value of k by doing the following simple math, dividing both sides of our equation here by 35. So I'm multiplying 1 over 35 on the left hand side, and I'm dividing by 35 on the right hand side. That's how we're doing the math sometimes. All right, and so now k equals 1 over 35 times 1 over 35 times natural log of 1/2. And so what this expression here is the exact expression for our value of the continuous decay rate right here. But I'm going to swing over to the calculator to get an actual calculated value in decimal right here. But this rate right here, according to our lecture about how we can write a modeling function, then this k is regarded once again as either the relative rate or the continuous rate here, and I mean the decay rate. Okay, relative decay rate or continuous decay rate, because we made it as a choice to make it to use the form of the function that's more commonly used out there among the scientists. So we went with that continuous model. And so here we're going to have to find out our continuous rate. Okay, so now on the calculator here, I'm looking at 1 divided by 35, and I'm multiplying that with natural log of 1/2. And this value is going to come out being, so it's negative and approximately 0.019804. I'm going to go with 5 decimal places. But so this is an advice for anyone when you're working with these problems. Watch out for your own rounding requirements in each of the problem that you're working with. Okay, so here I am going to round to 5 decimals. And so as you have seen it, the k value is a negative value. And so now our k here is negative point, and just consistent with what we agree here, negative point, and I'm running out of space here, so allow me to just skip the word k approximately. So approximately negative 0.019804. And I meant to say I'm staying with 6 decimal places here in this problem. But once again, watch out for your own rounding requirements. All right, so now upon finding, so our main aim of this problem is not to stop at deriving or writing the modeling function. So this is not our ultimate ending of the problem. This is only stage 1 of the problem. And so once we found the continuous rate here, the continuous decay rate of our problem, we are ready to put our modeling function together. We are now ready to complete our modeling function. But then we're going to move on to stage 2 to actually answer the question that was being asked right there, that was asked. Okay, so now I'm going to have to eventually erase the board, but I'm going to retain the actual complete equation of our modeling function. All right, so now we are ready to complete our modeling function here. That is Q of t equals 100 times e to the negative 0.019804 t. And as I said earlier, I was using 6 decimal places in this problem for my continuous decay rate right here. So that was the continuous decay rate that we have found. And so for this problem, I emphasize again, the time variable here is measured in hours. Okay, t is measured in hours. And so now arriving at our modeling function here, we are really ready. Okay, back to the problem itself. Now we can read the problem, and the problem is asking that how many milligrams will remain after 54 hours. That means now the problem here, the question of this problem is nothing but just evaluating the output of this function when t equals 54 hours. Okay, so that means, or mathematically speaking, or symbolically saying it, we want to evaluate q of 54 in functional notation. We want to evaluate the value of our quantity function here, okay, in 54 when t equals 54. All right, so now getting into the actual problem right here, q of 54 will equal to 100 being our initial amount times e to the minus 0.019804. 0.04, but substituted 54 for t. All right, and now in the next step, it's just a matter of swinging over to the calculator and punching the value for this to get a final the answer in decimals. Okay. All right, so now back on my calculator here, I'm looking at 100 multiply with e raised to the power of, now my k is negative 0.019804. Okay, and then I'm going to multiply that with t being 54. Okay, so this is from what was on the board earlier. Now I'm going to go ahead and hit enter. All right, so this is our final answer right here. That means in 54 hours, our radioactive substance remains only 34.32 milligrams. So when you're actually doing this problem as one problem that you are doing with the other scientists out there, then watch out for what they require you to write down as the number of decimals. In the lecture here, allow me to use, in this particular demonstration, allow me to use just 2 decimal places here. And once again, watch out for your own rounding requirements in each of the problems that you're doing. Okay. So now, approximately we have approximately about 34.32 milligrams. Okay, that remains after 54 hours. All right, so that's how, and so once again, this problem is one among the problems where we find or we estimate a future value. This is a value at some future instance. Okay, that's what it is. All right. All right, so now allow me to walk you into a different scenario. Okay, so in this scenario here, how about we are going to find or estimates again. We want to find or estimates we want to find or estimate the time the time to reach a value. Okay. When I'm saying the time, I mean, when we will reach to a certain desired value. This is another scenario to be introduced right here. This is one among the scenarios to be introduced. Okay, so let's get to it. So now I'm going to swing over the wording description of one problem here first. All right, so here we go. In this problem, let's read the wording description right here. Now, a company's sales can be modeled by the function S of t equals 5,000 times e to the 0.12t, where t is measured in years. Okay, and this is just the description of the data we have right here. We didn't see any question yet. But so, just like what I've been explaining, then with this problem again, we are about to work with a problem where we apply. Where we're looking at the application of an exponential function. So right here in stage 1, we already had the function given. We already had the modeling function given. So we simply just need to identify what that was. We don't have to write, in this problem that I'm showing, we don't have to write the modeling function. Nope, we're not writing the modeling function. We just need to identify that from the given information because it was given. All right, so stage 1 is already simplified for us. Stage 1 is already given to us. We're gonna, in our work, our job for this problem is to take the given function and make the predictions. make all kinds of predictions. And so now let's find out what that function is. The function is given to be in this problem, S of t. So if we're running a company, think about from first years, from the first instance that we open our company. Okay, sales here represent it could be the quantity that we're able to sell away, the number of units that we are selling away. So this is some initial amount of sales quantity, and then our sales is growing exponentially. Okay, and that's why it says, as it's stated here, the sales of that company can be modeled by the function S of t. So S stands for the sales quantity, equals 5,000 initially times e to the 0.12t right here. All right. So catching immediately with that given information. This problem, I have to make it clear. I have already identified our modeling function. It's given. S for the quantity. Okay. And this problem is a problem that exists among the business experts, the business professionals out there. Okay, so here pretend with me that you're one of those analysts or a business professional that's working on your own on the sales of your own company. All right, so S of t equals 5,000 times e to the 0.112 t. 5,000 times the e to the 0.112 t. Okay, so just something to put into our awareness, even though it's not directly important, it's not too important like that, but it's good, extremely beneficial to know. So this is the initial. So here, how about the initial sales amount? Okay, the initial sales amount. All right, and this is a continuous. And our problem here is apparently a growth problem. The sales over time, over years. Okay, our sales, our quantity, our sales amount is increasing. So I'm talking about this problem is putting us in a scenario where we're looking at cumulative sales quantity over years like that. So we started out being able to sell only 5,000 units, and then over time, over years, that sales is going up. It's a growth model. So this problem in general, base E, if you notice that, okay, if anyone watching the video has noticed that. So the whole problem here, we regard to this as a continuous growth model. Okay, yes, this is a continuous. All right, this is continuous growth model. So a growth model or a decay model is, we just have to be ready for any of those situations like that. But what we have here is a continuous model, okay? And in some other problem, we may be exposed to a decay model like that. But base E means it's a continuous model, and then that's the initial amount. So this 0.12 right here is the continuous growth rate, okay? And my board is getting tight, so I don't want to write down too much right there. All right, but now to get into the actual problem. All right. So after making some notes here about the problem, and we know that it's a growth problem, now let's look into the actual the question of the problem. All right, and so now with the actual question here, we will be having, so part A here is indicating that after this question there will be another one. So the question in the question A here, right from this problem, is asking us estimates when the sales will reach 8,000. Estimates when the sales will reach 8,000. We want to reach 8,000. All right. So think about the logic here. I mentioned it clearly according to the way how it is for this problem, and especially I noticed this is a positive rate here, positive continuous rate. Our function here is representing a quantity that's growing. So our sales amount is growing, and I stated it clearly here. It's a continuous growth model. So, and I highlighted it that this 5,000 as the coefficient here is being the initial sales amount. That means 8,000 is some future amount, some amount in the future. But now the question is, when? How much time, how many years will it take? How many years will it take to reach 8,000? How many years will it take to reach 8,000? Or in other words, mathematically speaking, this problem brings us to, we want to find t. We want to find a value for t. We want to find a value for t when s of t equals 8,000. It definitely is a future value. So that's why, when is that future? When will we reach that future value? That's why we're finding t when s of t equals 8,000. All right, so now once we set clear with that goal right there, we clearly see that goal right there. So in this problem, we don't estimate how much output's coming out in some t years later, but we're estimating how much time it takes, okay, to reach to a value right here. That's the idea. Okay, so right here, let's tackle down right here with that relationship right here. We want s of t to equal 8,000. We want s of t to equal 8,000. So that means in my problem, I'm looking at s of t is this function that's previously given or already given here. And so now I'm looking at 5,000 times e to the positive 0.12 t, and we are equating that with 8,000 because we want to find a value for t where this function s of t will equal 8,000. This is what we're looking for. This is our goal of the problem right there. We want s of t to reach 8,000. That's why we have that equality. And then s of t equals 8,000 consequently produced this equation for us. And now all of a sudden we realize. So this is needless to say, but arriving at this video lesson, you must, and for anyone viewing this lesson, upon arriving at this lesson right here, you must have already watched the video lesson where I showed how you apply logarithms and all that, especially that skill about how you can apply logarithm to solve an exponential equation, because it's right here. Okay, because this is an exponential equation right there. Okay, this equation is an exponential equation. So my first step into solving this exponential equation, we simply just going to divide both sides of this equation by 5,000. Okay. And then that brings my equation down to that reduces my equation to e to the 0.112t to equal an 8/5. I mean, I don't always have a calculator immediately in hand right now, so I tend to work with anywhere I still can, I tend to adjust my style. You're not required to follow with that style of mine, but here I'll just go with fraction for now, and then at the final step, I'll punch it in the calculator to get the final numerical outcome. Okay, so now I'm looking at, as far as equation, I have reduced my equation down to e to the base e to the 0.12t equals 8/5. E to the 0.12t equals 8/5. So ladies and gentlemen, this equation is clearly an equation in exponential form. So we can now easily rewrite this equation or re-express this equation as an equation in logarithmic form, and that's where we have already spent some good amount of time learning how we can apply logarithm to solve an exponential equation like this. Okay, so now it's giving me, in the next step, I can rearrange this equation as 0.12t to equal logarithm or natural logs precisely of 8/5. Okay, so 0.12t equals natural log of 8/5. So that means now I can just simply divide both sides of this equation to end up with t equal natural log of 8/5 divided by 0.12. That's how I'm doing it. My board is narrow here, so allow me to skip showing that step of dividing that 0.12 from both sides. That's what I did to arrive here. All right, and so now we simply just gonna swing over to the calculator and punch this in right here. Okay, and punch this expression right here into a calculator to obtain our, or at least the estimates of how much time it takes. And t in this problem, I should have also noted that t is measured in years. So upon calculating this, it's how many years approximately it will take, okay, to reach 8,000, in the sales quantity right there. All right. All right, so now on my calculator here, we're looking at 1 divided by 0.12. All right, 1 over, because divided by 0.12, and then I'm multiplying that. That's another way of working around on the calculator. Now, natural log of 8/5. And this is our final answer right here. This is our final answer. So I'm going to go with, so it 3 point, and I'm going to round to 2 decimal places. So it's nearly 4 years right there, nearly 4 years right there. The question here did not specifically ask to go with whole value number of years like that. So we can go, because 3.90 something years means we're way more than 3 years, but still a little bit less than 4 years. Maybe 1 month less than 4 years, something like that. Okay, and so now t is approximately, or t is about 3.92 years, or approximately 4 years like that. Okay, the problem illustrates the idea, but when you are actually in your real context of the problem like that, then every problem has a different rounding requirements like that. So keep an eye on your own problem when you're working. Either you are hired to work with these problems, or you are working with your own problems as you are studying. Okay, so in this particular problem here, I'm doing on the board here, I go with 2 decimal places. So it's t is about 3.92 years. Okay, years. All right, so that's the answer for this part A of our problem like that. And now the same problem, we have another question to look at. Okay, so question B here, and so I label these questions when I'm organizing these problems right here. Even in the same problem, when I call that part B or part A, these are just 2 independent problems. We don't have to, meaning we don't have to know the answer of question A in order to answer the question in B, or we don't have to know the answer in B in order to answer the question in A. So that's what I meant. It's just according to the order of the questions that I'm going over in this particular problem. Then this question here comes after the other question. So I just treat it as part B of the example. But any one of question A or question B, they are 2 independent problems, or 2 problems independent from each other, and they both take information out of this given information right here. So that we're still working with that same company where the sales is growing according to this model. So 5,000 e to the 0.12t. Okay, and now we want to find out how long. See, and once we know that t is measured in years right here. All right, so how long does it take to double? This word here is to highlight right there. How long will it take to double the initial sales quantity? The initial sales quantity. So, simply seeing this as just a different problem, okay? It has really nothing related to the problem we have done in part A. One problem that's completely independent, okay, from the result we have found in part A. But both problems draw information out of this equation right here. And now this is where it's beneficial that we have identified a couple of information from this equation earlier. This 5,000 that I underlined right here is called the initial sales amount, or the initial sales quantity. Okay, and yes, this is a continuous growth model. Okay, and because we know it's growing, the sales quantity is growing, the question was asking, how long does it take? How long does it take? Okay, so how long? We want to find t again. We want to find the value of t. Okay, the question was asking how long does it take to double the initial sales quantity. Again, one more time, let me show that on the computer screen right here. How long does it take to double the initial sales quantity? Okay, and so now knowing or being able to identify the initial sales quantity right from our function is a huge plus right there. So in another way of saying, find t when S of t, the sales quantity, double of the initial quantity, double of the initial sales quantity. That means it's 10,000, because initially it was 5,000 as a sales quantity. So we want to find out how long it takes. Find the value for t. How many years approximately, or about how many years will it take to reach a sales quantity being 10,000? That's what it is right there. Okay. How long does it take to double the initial sales quantity? I mean, there are so many different interpretations about the problem, but in the way how I'm putting it is for for anyone who has the minimal amount of math background can still understand. Okay, but there are other ways, different ways of interpreting the same problem, like that, the same way how the question is asked. Okay, so now just like that, so all of a sudden we realized, the reason we call it part B is it works just very similar to how we've done it in part A right there. All right, even though the two problems are completely independent. Okay, but the way how they work, so now I see this as a repeated practice of the problem we have done in part A. All right, I want S of t equals 10,000. So that consequently produced for me 5,000 times e to the 0.12t. This is S of t. I want S of t to equal 10,000. I want S of t to equal 10,000. That's how I consequently produced this. And so to solve this equation, I am going to divide both sides of this equation by 5,000. And doing that will take me to e to the 0.12t to equal 2. E to the 0.12t equals 2. Okay, and so again, here's another way. Here's a different way how I see the two problems that are given in this particular, the two questions that are given in this particular problem we're going through right there. Okay, I just want to set a standard, even though it's not the fastest way, but it's the most understandable way. I just want to set a standard that, hey, anytime we're doing this kind of problem, estimates the time it takes to reach a value. Either the value there is a double value, or it's just some percentage of value increase right there. We just always want to start out by setting our functions, our previously given function or a previously found function, modeling function, to equal to that future value. And then from there we produce an equation. And then from that equation we're going to solve. Okay? And so now reducing the equation will lead us into this form. And now this form here is clearly an exponential form of our equation. We can now rewrite the exponential form of the equation here into logarithmic form. So now I'm looking at 0.12t equals a log base e of 2. So the steps are exactly the same, or exactly the repeat of those steps found in problem A right there. So using the term double or not, it's just different fancy ways, but there's one standard. I'm not saying this standard is the fastest way of getting your answer, but it's the most easy to understand. And it reflects directly the philosophy of this problem right there. It comes straight out from the philosophy of the problem right there. Okay, and so now 0.12t equals natural log of 2. I'm going to divide both sides by 0.12. Okay. And that now will give me t equals a natural log of 2 divided by 0.12. So whichever value that comes out from this expression right here, natural log of 2 divided by 0.12, that is approximately the number of years it takes to double the initial sales quantity right there. All right, so now I'm going to once again swing over to my computer station right there and show the calculation steps with my TI calculator. Okay. All right, so now on my calculator, natural log of 2, and I'm dividing that by 0.112. This is how many years it takes approximately, or about, this is about how many years it takes to double the sales quantity from 5,000 to increase, to grow the sales quantity from 5,000 to 10,000. That's another way of saying to double, but this is how much time it takes, about how many years it takes. All right. So now on the board, I'm saying that it takes about 5.78 years. Okay, a little bit more than 5.5 years. See it that way in the practical meaning, about 5.78 years. Okay, to grow double of the sales quantity. Okay. Is that a fast growth or a slow growth? That depends on the judgment of whoever the real person who works and analyzes this data. All right. All right. So we're still working with those problems. We're still working in that scenario. In this scenario where we want to find or estimate how much times or the time to reach or when to reach a given future value. Okay, so allow me to introduce another problem or one more problem. Okay, so let's turn over to the computer station right here to the worded description on the computer station. Okay. All right, so in this problem, the wording description says, and this is really one problem. So let's spend some time reading it, and then I will show how it's broken down into steps. So as just one complete problem, it took about 1,172 years for 20 milligrams of radium-226. This is the name of a radioactive element here. Not that radioactive, but this is a name of a chemical element here, radium-226, and an actual scientist or chemist refer to this as a radium isotope. Okay, but then so we have 20 milligrams. It took about 1,172 years for 20 milligrams of radium-226 to decay. So this is now a decay problem. That's the wording that caught my attention. So it takes that many years, or it took that many years as scientists discover. Okay, it took that many years for 20 milligrams to decay to 12 milligrams. Okay, so we can think of this as some initial time, some initial amount and some final amount right here, and we know that it took that many years, and so immediately after that description, and that was the only description, we want to find the half-life of radium-226. And then after that question, we have another question. How long does it take? So the worded description missed a word right here. How long does it take for 20 milligrams of this element to decay to 1.5 milligrams? So now, apparently, this is a decay problem. It's a decay problem. It's an exponential decay problem. Okay? But in this problem, as far as aligning our steps with the general guideline here, I see this as general guideline or just a certain general order of how we get the steps done. And so as far as stage 1, we don't even have the function. We didn't even have the function given on the computer screen. We didn't even have the function given. Okay? Instead, we had some description of whatever scientist or the chemist have already recorded. So some long time ago chemist discovered that it took that many years, 1,172 years, for 20 milligrams of radium-226 to decay down to only 12 milligrams. Okay, just to lose 8 milligrams, it took 1,172 years. Okay, and we know that chemical elements, or a lot of times, or most of the time, or not only just most of the time, we always decay exponentially. It will lose itself or reduce itself or reduce itself exponentially. Okay, but now back to stage 1 right here. We have to find write the modeling function based on the data given, because we didn't have the function given. Okay, so what matters? So in this particular situation or in any particular scenario, what matters is about whether we have the function given. If the modeling function is already given, good. Okay, take on with that function and move on to the next step, step 2. Okay, do all kinds of prediction. But in case that the function is not given and the problem did not specifically ask for that, but we know it is our responsibility to write the modeling function. So step 1 is always a big door, a big must to get it done before we can move on to step 2, to stage 2. Okay, and so just like what it said right here, and just like what I said when I was on the board earlier, the problem itself did not ask specifically to write the modeling function, but it is our responsibility to extract the data, the information from this, from whatever highlighted here, okay, to come up with a modeling function. And then in that way, once we've had the modeling function, now we can make these predictions. Okay, all right, and so now just before we get really started, this term half-life, I have had some explanation of what that is precisely in my video lecture that I taught about how we write a modeling function. But briefly, it's half-life means the time it takes, how many years it takes for radium-226 to reduce down to only half of the original amount. So think about if we treat this as the original amount, then we want to find out how many years it takes to get down to only 10 milligrams remains. Okay, all right. So now in that way of how I'm explaining, allow me to break down. Admittedly, this is one whole problem, but allow me to break down the information one by one here. Just right here in the main description. And the question did not ask us, again, the question did not ask us to write the modeling function specifically. But now I'm going to just simply read right here, and I'm going to extract the information from right from this beginning description of the problem right here. It took about that many years for 20 milligrams of radium-226 to decay to 12 milligrams. I am now going to use that information to write the modeling function. Now, the wording was making it clear that it's a decay process. It's a decay process, an exponential decay process. Okay? And so, again, I have explained this in my lecture when I was showing how to write a modeling function. We will always have two different choices, whether either to go with a periodic model or a continuous model. Whether it's a decay process or an exponential growth process, we can always write two different versions to produce the exact same result, but we can always have the different versions of our modeling function. But I will head out for the continuous model, and again, simply because it's being a lot more commonly used among the actual scientists out there. Okay, and so the continuous model in this case is in the form of Q of t equals initial amount Q times e to the kt. And knowing that this problem is an exponential decay problem that's awaiting for us, then the k value here, once we have found it, it must be a negative k, because it's a decay problem. If it's a growth problem, then it's going to be a positive. Okay, so again, my plan is to stick with this continuous decay model, simply because it's I brought in that understanding about base E is the winner, because it's it's not only because if it's financial math, and base E is the one that brings up the most income after interest, but for scientists out there, then base E is the one that's most commonly used, and that's why base E is the winner, even though we have a lot more choices out there of the base, but we want to stick with base E most of the time, or most commonly. All right, so now with this problem right here, now we're setting up for ourselves a general form. Our function here as an exponential decay model must be Q of t. This is the initial amount times e to the kt, where once we have found it, it must be a negative rate. And again, this rate, just as a reminder, even though it's not important here, this rate here must be regarded as, must be called the continuous decay rate. Okay, the continuous decay rate. All right, so now let's swing back to the problem and identify some more data like this. So it took about 1172 years for 20 milligrams of radium-226 to decay to 12 milligrams. It takes that many years for 20 milligrams, okay, to decay to 12 milligrams. So I said it earlier that we can think of this as some initial amount, and this is some final amount after that many years. Okay, again, we can take that simply in just the way how it's described, and just with standard English wording like that. Okay, we can just treat this as some starting amount, some initial amount, and this is some final amount over that long period of time, 1172 years. All right. So in that way, in the way how I see it now, Q sub 0, the initial amount, can be simply regarded as, or can be simply let equal to 20 milligrams, because that's how much we started out. And then from that point on, scientists noticed it took that many years, okay, more than 10 centuries, 11 centuries actually, okay, more than 11 centuries to decay to, so from that 20 milligrams, it takes more than 11 centuries to decay down to 12 milligrams. So we can legally call that 20 milligrams right there the initial amount. And so immediately, as an impact right here, Q of t equals 20 times e to the kt. All right. And so at this point, we're going to start applying our understanding in terms of how we can write. And we've learned all the skills. We should be familiar with all these steps here from the lecture where I deliver how to write a modeling function with the continuous model, using a continuous model. Okay, so now this is where I call it a halfway done, continuous decay model for us here. So now in order to find what we know here as far as given information, okay, we're looking at, we know that Q of 1172, because time is in years, it takes that many years, it took that many years to reduce, to decay down to 12 milligrams. So in other words, this is what we're given. All right, so from what we have understood, this Q of 1172 means our left-hand side here becomes 20, or substituting this 1172 into the function Q of t, we're looking at 20 times e to the k times 1172. Okay, that's just substituted in, and all that there is equal to 12. That's right out from the given information. Okay, and so how do I know to use this model? It was all explained in the general lecture. In that lecture where I taught how to derive with a modeling function, how to write your own modeling function, specifically using the continuous model. Okay, so these are, and these steps were quite standards, and they were already all taught in that particular lecture. Here it's just, I'm gonna, speeding up a lot faster than how it was in that lecture there. Okay, so now with this, I can rewrite it as 20 e to the 1172k to equal 12. And now I can divide both sides of this equation by 20. And that will reduce my equation to e to the 1172k to equal, this is a 3/5. This is 3/5. All right, it's a 3/5. Because 12 over 20 is reduced to a 3/5. And so now this equation here is an equation in exponential form. we will rewrite this equation in logarithmic form, okay, and to obtain for ourselves 1172k equal natural log of a 3/5. All right, and now with this, once we have arrived at that step, I can easily solve for k here by simply dividing both sides by 1172. Okay, dividing both sides by 1172. And so now it's just a matter, our k value is simply just a matter of punching that value into the calculator. And so in the next step, really, it's just about canceling out, because 1172 on the left-hand side. So in the next step, really, I'm out of space here, so allow me to skip that next step right there. But instead, I'm doing that dirty little trick right there, just erasing and write k equals all this. So now I'm going to swing over to my calculator to obtain the value for k. Okay, and so it's a decay process, so I am expecting that my final answer here is going to be a negative value. Okay. All right, so I'm just getting that ready for my actual k value after I've got it from the calculator. All right, so on this calculator, here we go. Natural log of 3/5. All right, and now I'm going to divide that by 1172. That is my final answer. And so quite sometimes the calculator will display at least with the TI-84. At least in the TI family of the calculators right here, this e minus 4 means times 10 to the negative 4 power. So this answer really means a negative. So on my board, it's that answer there means it's negative 4.35858, and a lot longer, but times 10 to the negative 4. So it really means in real decimals, it's negative 0.3 zeros, and then a 4, and then 3, 5, 8, and then allow me to just, that last digit there is a 6. Yeah. Or we can just round to whichever the rounding that whatever your problem is requiring you to. So in this particular problem, allow me to go up to that many decimals. Yeah. Okay, because the longer the decimal is, the better precision is going to reach for us. That's all there is. So this is okay, and it's negative, indicating that it's a decay process. So now we are ready to complete our modeling function. And so you got to be aware that this is even before we actually get into any of the problem. We just have to, even though we're not specifically asked for it, but we just have to get our modeling function. Okay, we just have to get our modeling function. And so now, completing our modeling function, it looks as following. So now our modeling function is q of t equals 20 milligrams as start, initial amount, times e to the negative 0.00435886. Okay, that many digits in my decimals, 0.00043586 t. That is our exponential function that models the amount of radium-226 that remains in some t years. So yes, t is in years. All right, and now upon getting this function completed, this modeling function completed, we are ready to answer our first question. All right, so now back to our problem number this. All right, so now back to the problem itself right here. Let's advance to the first question of the problem. So now, after we get the function right here, now in the first question, and I call that question part A, And then expectedly there will be another question, but then the two questions are not really related to each other. They're just the two questions are not really dependent on each other, or in other words, they are just two completely independent problems, or two problems completely independent from each other. So in the first question we're looking at here, based on the function we have already found, we want to find a half-life of radium-226. Okay. So now we're about to find the answer we're back in that kind of problem where we want to estimate the time it takes to reach a value right there. Okay, and then we have already found our modeling function, even though it was not specifically asked in the problem. Okay, and now we're going to use this function, and we're going to use that to find how much time it takes to get to only half of some initial amount. So the term half-life that was mentioned in the wording of the problem right here, half-life means the time it takes to reduce from whichever initial amount to only half of that. All right, so in this problem right here, in our problem right here, so now with this function that we have already found, then 20 is considered as the initial amount. So this is initial amount. All right, so now knowing this initial amount right here, we want to find half-life. And just as I stated earlier, half-life is the time it takes. How many years it takes? Okay, because t is in years here. How many years it takes to reach to only half of the initial amount. Whichever initial amount it could be. Whichever initial amount it could be. In some other problem, we can be starting out with 100 milligrams. Okay, but how long does it take to get only half left? So now our initial amount for this, for radium-226 is 20 here in this particular problem. Okay, so now to find half-life, that means we want to find the time. Okay, we want to find a value for t. Okay, when our quantity, okay, at that time right here equals only 10, because it's half. It's the time, half-life is the amount of time it takes to reduce from some initial amount to only half. So here we know that in this particular problem, and certainly it is, particularly it is already about, in this problem we're learning about radium-226. But whatever starting amount with radium, some other scientists may study with only 10 milligrams at start. How long does it take to get to only 5? Our problem here, we're studying 20 milligrams initially for radium-226. And how long will it take to reach to only 10? So basically, how long will it take to reach to only half of the whatever initially present there? And that's why it was good that we underline that with red ink right here. So now we know that when it reached to the output value being 10 right here, how much time does it take? That's the idea. All right, and so now immediately after I pointed that out, and anyone watching the video should now have an idea for yourself. Okay, so now we want Q of 10. We want the function outputs to equal 10. So that means but the function outputs, just like how we've been learning about solving equation, then the function outputs, the function itself is 20 times 20 times e to the minus 0.0004356 t. That's the function. And then we want that to equal to 10. We want the output of this function equals 10. And then from there we are going to solve for the value for t right here. Okay, we want to find t from this equation. All right, and so now I am going to divide both sides by 20. Okay, it's just standard step. We're dividing the coefficients away. So I'm gonna end up with e to the minus 0.0004356 t. That's exponential function to equal with 1/2. Okay, and so now at this point, I notice that what I have reduced to is an equation in exponential form. Okay, an equation in exponential form. So now, well, after we have learned in detail enough about how we can rewrite an equation in exponential form, in logarithmic form, then the next step of my equation, I can rewrite it as following. So now I'm looking at the exponential part right here, the part in the exponents right here, can be rewritten as minus 0.0004358 times t. All of that there equals a natural log of 1/2. Natural log of 1/2. All right. And so now in this case here, I'm ready to solve for the value of t. So I'm going to divide both sides here by negative 0.0004586. And I do admit that my board is getting a little tight right here in space right here. Okay, so negative 0.0004358. All right, and so that now means t has to equal, okay, whichever comes out from natural log of 1/2 divided by minus 0.000. Okay, 43586. All right, and so all it matters now is just punching in the calculator, punching this expression into the calculator, and get a final value in decimal or whatever. Okay. All right, so now on my calculator, we're looking at natural log of 1/2, and I'm dividing that by a negative quantity, negative 0.0004586. All right, and now let's hit enter. So the answer comes out being this much. All right, so 1,590 and 0.29 or 0.30 if we round it to 3 decimal places, years. Okay. And so now mathematically speaking, it takes about 1,590.3 years. That many years for only 20 milligrams. 20 milligrams in our daily life is very little. And it takes that long for 20 milligrams of radium-226 to reduce to 10 milligrams like that. Okay, but now take my word on this. This is just in case anyone outside of this lesson is heading out for a formal chemical study, for some study in chemistry right there, then chemists usually round this number to a whole value. So in this case, it's 1590 is, among the chemist community right there. Then they use they standard that as a 1590 years like that. Okay, so this is the number that you see in a lot of chemistry textbooks right there. But mathematically speaking, right out from this information, then it's about 1590.3. But just in a matter of that many years, and 0.3 is not going to be making too much difference. I mean, to the point of being neglectable. Okay, so you can go either with that decimal into decimal places or go with the rounding. So once again, that's why I was saying if anyone is intending to go into a chemical field right there, then be aware that we have this number. So it's all about how far you need to round right there in each of your problem. Okay, and so that's another problem here. That's a problem that shows you, that puts us in that scenario where we want to estimate, or we want to find how much time it takes to reach to a given future value. I mean, I didn't write it here, but it's a future value. Okay, either it's a growth or it's a decay. The problem we have here is a decay problem, but it works the same. It works similarly with a growth problem right there. And at some point, we will have to use a logarithm to solve for the time variable right there. Okay. So let's look into the next problem after I erase my board. All right, so now back on the problem itself right here. Let's head out to part B. And so now from the same information here, we have already found for ourselves the modeling function. Okay, and now with that modeling function, we have another question. So again, just as I have said earlier, the question A or question B, in the way how I organized the problem, it made it look like the two problems are related with each other. Oh well, yes, they are related to each other through the fact that they both draw information. They both draw information out of this equation right there, out of the beginning description. But in the end, those two problems are really the two independent problems. Okay, we don't need part A in order to get part B done. We don't need part B in order to get part A done. Okay, those are just two independent problems that the order of A and B doesn't really matter, and that's what I'm trying to point out right there. Okay, and so now back in the problem itself, now it's asking, and the wording here is making it real clear with what I have described here. The scenario that we're at right now is that we want to find how much time it takes, okay, to reach a certain value right here, either our model, our growth model, or our decay model, like that. All right. So now the question in B here is asking how long does it take for 20 milligrams, okay? And again, I had that, as I admitted earlier, I had the problem itself has a little the missing word right here, but how long does it take for 20 milligrams of this element to decay to 1.5 milligrams? How long does it take for 20 milligrams of this element to decay to 15 milligrams? And so again, we're treating this here as the initial amount, just like we have already agreed. But we want to finally arrive at 1.5 milligrams. Okay, so see, the destination here, we want beginning value or initial value, we want final value right here. And we want to find how much time, so we want to find the value for t. All right, and so now again on my board, here's how I'm categorizing the problem right here. So we want to find t, okay? We want to find t when q of t equals 1.5 milligrams. It's a long process going. I mean, maybe if we really want to see how problem B connects to problem A, then just think about if we have done problem A before problem B here. It took 1,590 years, a little more than that, to go just from 20 to 10 years, to go halfway of the amount. But now this is only 1.5. That means it's going to be a lot longer. Okay, let's see how it's done. Let's see how it's done. All right, so we want to find t when q of t equals 1.5 right here. And another way of wording this, we can also say find t satisfying q of t equals 1.5. I could have also brought this up into the earlier part of this of these problems right there when I was introducing it earlier. All right, so now back in our problem, we want q of t equal 1.5. So now I'm looking at, but q of t is this function that we previously found. We found that even before we got into answering any of our questions. So now 20 e to the minus 0.0043586 t, but we want that to be equated with 1.5. That's how we're doing it. That's how we're tackling down the problem right there. All right, and so now I'm going to divide both sides by 20. So the steps now look, and any one of the steps here looks pretty repeated from the earlier problems like that we have done. And so now we're looking at e to the minus 0.0043586, and that equals to, so 1.5 over the 20 right there. Okay, and we can leave it like that, or in fraction, this is 3 over 40. All right, so in my next step right here, we're looking at this equation, since it's now currently in the form, it's reduced to the form of an exponential, it's an equation in exponential form. Then in the next step, I can rewrite that as an equation in logarithmic form. And so again, just like what I said earlier, any one of the steps here that we're seeing here is pretty much a repeat of some work we have done earlier. Okay, and so now here I'm looking at I missed a t right there. So negative 0.0004356 t to equal natural log of 3/40. All right, and so now we're just going to divide both sides by negative 0.0004356. Okay, negative 0.0004356. All right, and so we will end up with whichever comes out from, so the left-hand side here cancels all that ugly looking decimals there. So now t should equals, as in precise expression, natural log of 3/40. Okay, and divide that by minus 0.0004356. All right, and so now it's just a matter of punching this expression into the calculator and get a final numerical outcome for that. All right, so now on my calculator, natural log of 3/40, and this calculator is strong enough to do that all-in-one command right here. Divide that by negative 0.0004356. All right, and here's the answer: 5,942.89 if we round to 2 decimal places. All right, so that means it takes that many years in approximate value right there. Okay, approximately that many years to decay from 20 milligrams down to only a 1.5 right there. All right, so that means this is approximately 5,942 in 2 decimal places, 89. All right, and so now I'm using 2 decimal places in my particular problem here in this lesson here. But when you're actually doing this among the scientists out there, make sure you watch for their own rounding requirements. Okay, and or at least the rounding the agreements among the scientists right there out there. And when you're working on your own math problem, also make sure to watch out for the rounding requirements of your own problem right there. So here, we're looking at, and I just now noticed I had a typo over here, 5,942.89. Okay, but now here I'm using 2 decimal places. Okay, and then there's quite a few standard textbooks. So they're using for chemistry they're using 5,943 right there years. But these are in years. This is the number of years it takes. That many years to decay from 20 milligrams down to only a 1.5 milligrams. All right, but generally speaking, this problem right here, this particular problem right here, we're in that scenario where we want to find or estimate how much time it takes, okay, to reach a specific given value. All right,